So today I want to talk about continuity. And I have two reasons for that. One is because continuity is a beautiful and absolutely crucial topic in mathematics, as we'll see. And the other is because this video represents a kind of continuity for me. I have finally bitten the bullet and purchased a proper blackboard for my home. I don't think I'm going to be getting back to my office anytime soon to continue that setting for filming, and so it's time to move on from the sort of cheap little board that I had been using before and start going back to the types of videos that I started doing when I began this channel. So continuity for two reasons. Now, mathematically, back to the math here. What is a continuous function? And let's focus on functions that take inputs that are real numbers and outputs that are real numbers. So these are the kinds of functions that you can graph on an XY plane. I have another video about graphs if you want to brush up on that. And the sort of canonical example of a function that isn't continuous looks something like this. What I've drawn here is what's often called a jump discontinuity. And the idea is that here we have this function, it's going along, minding its own business, and then all of a sudden, at this point, let's call it A, it sort of makes a jump, or at least when I graph it, it looks like the graph made a jump. And this is supposed to be, this is an example of a discontinuous function, and it sort of gives rise to this intuition that's often put forward in high school math classes, that continuous functions are the kinds of functions that you can draw the graph of without taking your pencil off the page, or without taking your piece of chalk off the board. Okay, so it would be something where each point is pretty close to the previous point, so I can draw it as one continuous line, right? It doesn't have to be smooth, it can be like this. This looks like this is a continuous function too. The point is that it doesn't have like something like this, like a jump, right? Or some kind of more general way of behaving badly. So we're just talking about intuitions here, but I want to get a little bit deeper into the intuitions before we get to the official definition, because the official definition of a continuous function is a little bit monstrous. It's the kind of thing that strikes terror into the hearts of students when they first see it. And I actually want to present it as something very intuitive. And to do that, I want to move away from this pencil on the page intuition, which is fine as far as it goes, but I want to go to a sort of a more pointed intuition. And that intuition can be summed up by saying continuity is essentially a form of control. What do I mean by that? Think of a function as a machine for taking an input, x, and transforming it into an output, y. So you take an input, like say this input, and it transforms it into this output. So this input becomes this output. This input becomes this output. Continuity is a notion of control, because what continuity is saying in a function is as long as I exert sufficient control on the input to the function, I can get as much control on the output of the function as I want. So by controlling the input to the function, I can control the output to the function. And if you look at this jump discontinuity, this example of a function that's not continuous, and it's really right here that it fails to be continuous, we see exactly that idea of control breaking down. If my input is A, then my output is this point up here. But now, A is a completely infinitely precise input. What if my input isn't exactly A? It's just something kind of close to A, something in this neighborhood around A here, something in this range, this interval. Well, if it's something a little bit to the left of A, right, then the output is something pretty close to what the output was before. So as long as I'm pretty close to A on the left, my output is pretty close to what the original output was. So that part checks out. On the other hand, if my input is just, by accident, a little bit to the right of A, maybe it's A plus 0.0001, then the output suddenly, because of this jump, is way down here. And that's far away from what the original output was. I can label this as f of A. The output when I input exactly A is up here. The output when I input something very, very close to A but to the right of A is way down here. So the jump, the thing that looks like a jump in the graph, is really an instance of lack of control. Okay? No matter how tightly I try to control my input, as long as it's even a little bit off and to the right, I get an output which is way off from the target output of f of A. So that is the intuition that the definition of continuity that I'm going to give you captures. And as with the definition of limits that I did in a previous video, we capture this notion of control using quantifiers. So, let me write it down officially. A function f going from R to R is continuous at A if, so I'm saying I want to write down the definition of what does it mean for a function to be continuous at a point. And the answer is, like I said, the intuition at least, is as long as my input is sufficiently close to A, my output is going to be as close as I want it to be to f of A. So this is the famous epsilon-delta definition because of the variables that I'm going to use. How do I write that down? Well, I start with this idea of wanting the output to be as close as I want it to be to f of A. How do I get as close as I want it to be? With a universal quantifier. I say for every epsilon greater than 0. And you should read this as saying for any degree of control I want on the output. That's how it's going to be used. So think of epsilon as a degree of control, and the smaller epsilon is, the more control I'm exerting. For any degree of control that I want on the output, there exists a delta greater than 0, which is to say there is a degree of control I can exert on the input, such that as long as I exert this much control on the input, I get this much control on the output. And since this is a universal quantifier, it's saying no matter how much control I want on the input, there's a way of getting it. There's an amount of control I can exert. Sorry, no matter how much control I want on the output, there's a way of getting it. There's an amount of control I can exert on the input that guarantees that. So how do I write that? You write it by saying for any x, which is for any potential input to the function, as long as x is within delta of the target input, which is A. So as long as x is within delta of A, remember delta is the degree of control that I can exert on the input. So think of this as saying as long as I actually exert delta much control on the input, so my input x is delta close to A, which is my target input, it follows, this is an implication, that my output, f of x, is, this is f of A, within epsilon of f of A. So the output is within epsilon, which remember was the desired degree of control, of the target output, f of A. So this long string of symbols here, this is the famous epsilon-delta definition of continuity. It's not something that I would ever recommend just memorizing as a random string of symbols. I don't memorize it. That's an exercise in futility. I mean, you can do it, but what you really learn from is understanding why these symbols in this order capture the idea of control. So one more time, what it's saying is, no matter how much control captured by this variable epsilon, no matter how much control I want to exert on the output, I can achieve that by exerting this much control. There's an amount of control that I can exert on the input which achieves it. And by achieves it, I mean as long as my input is this close to the target input, delta close to the target input, my output is epsilon close to the target output. And here, of course, I'm using the absolute value bars with the difference inside to capture distance, which I have another video explaining why that works. So we've got quantification used to give sort of mathematical substance to this notion of continuity as control, controlling the output by controlling the input. And continuous functions are exactly those functions that are useful in that way, that as long as you can control the input, you can control the output. And discontinuous functions are ones where, you might control the input, but it doesn't guarantee you have control over the output. Not in this sense. All right, so I hope this is what sticks in your mind when you think of continuity and not some abstract sequence of symbols or a vague intuition. It's the concept of control.